Good evening to everyone. I am going to give you a quick intro to Mike Barker. Mike is a consulting engineer and a building services specialist that is quite familiar to many in the South African Institute of Electric Engineers. He's been involved in building services for over 30 years in control and communication systems for the built environment. He holds a BSc in electrical engineering from University of KwaZulu-Natal. Mike has worked on many Southern and East Africa sustainable buildings, including the Durban Cape Town International Conference Centre stadiums, and for example, the Valpre LED Gold office in Heidelberg. He works with overseas organizations on extensive and ongoing research into the design and operation of high services buildings, and including the new generation of smart buildings and smart cities, of which there are many specs emerging and already established. In addition to his building services experience, he consults on sustainable buildings and energy efficient campuses. We started looking at building energy models because it appeared that it might be a very interesting way to develop planning models for certain classes of building within the South African distribution planning context. And that conversation with Mike grew, and we started to make connections with the overseas groups as well as our friends in EPRI. And that discussion is growing and it's ongoing. Mike has got some really interesting stuff to say, and I think we should hand over to him now.
Good evening to everybody, especially I believe we've got somebody from Zimbabwe, somebody over in Canada, must be early morning in Canada maybe. Anything in the built environment, any element can be modeled, right? Apart from energy modeling, we can model just about anything that you can think of in the built environment. And one of the first models that we did way back 10, 12 years ago was to try and understand how we can help the people in the townships and possibly see if a sprinkler system could prevent the spread of fire. So let's just have a look at this. We put together a couple of models of the buildings, the fuel load, the mechanisms that dictate how things burn. And we came up with this model over here. All right, we set it on fire and we let it burn. And you can see the fire started to peak at 800 megawatts before the sprinklers kicked in. It hit that line of sprinklers. There were no sprinklers in the top right-hand corner, and the fire crept around, as you can see there. Right? So this is using a package, an American package from NIST. It's called Fire Dynamics. It models crumbs, chemical reactions, the physics of burning, combustion, just about anything you can think of. Now, the interesting thing is that last year, the guys down in Stellenbosch, in the Cape, Stellenbosch University, working with the guys in Scotland, one of the Scotland universities, went and laid out a small little township. And they set it on fire to see how it burns. And I'm looking forward to getting some of their data to see how we can calibrate models, our models. So indirectly, this is an energy model of sorts. Okay. Next up, we set a container of lithium batteries on fire over at Rocheville, Eskom Rocheville, for those of you who know that area. We wanted to see whether any toxic smoke would reach the residential neighborhoods. Energy again, I think this was about a container full of lithium-ion batteries. I guess it was about a 40 megawatt fire. And probably more of interest these days is our colleagues over at ASHRAE are now modeling airborne particles from viruses, bacteria, etc. And you can imagine that this is probably one of the priorities. ASHRAE has just issued a set of directions, guidelines on preventing the spread of airborne diseases. So, you know, you could model just about anything. It's a combination of physics, a combination of energy. In fact, we tend to call ourselves building physicists. And of course, you're going to be asking, who's we? Who's this we that we keep talking about? And clearly, it's the International Building Performance Simulation Association. We just call it IBPSA. IBPSA has been around since '85. IBPSA has been growing ever since then. We've got about 8 to 10,000 active members around the world. A lot of members coming out of China, out of India these days, Brazil as well. And we get together every 3 years or so. And our last conference got a funny title, BS, but I can assure you there's no BS behind building simulation. The last conference, there were about 1,000 delegates, 660 research papers. And every one of these research papers since 1985 are available free on our website, ibipsa.org. Okay, so for my sins, I'm a committee member on the marketing side. I run various social media groups for IBPSA, and you can take part and learn more about energy modeling or about any modeling. It's not always about energy, as you've seen. So what exactly have I been and my team been modeling? Well, we've modeled a number of buildings in Africa. The first LEED gold office, the first LEED factory about 10 years ago. And since then, we're starting to tackle the new LEED version 4, which is one of the toughest, in fact, the toughest certification scheme for sustainable buildings. And this is this building here on the right. You probably can't see my cursor. Marcus, can you see the cursor, just by the way?
Okay. Mike, no, I can't.
Okay, fair enough. Right, so the building on the right there has this, it's in Nairobi, right on the equator, and we've put this convex roof on top of it, which is lined with bifacial solar panels, because just about every sustainable building these days has integrated photovoltaic systems. So we're looking forward to getting this one up and going. It'll be the first version 4, which is a very strict approach. As you know, the United States Green Building Council is the 800-pound gorilla in the game. They've certified about close to 100,000 buildings around the world, and including any famous building you've heard of, Empire State, Taipei 101, you name the building, and if it's a green building, it's probably a LEED building. Okay, so that's what we get up to. Now, there's this old English guy, Winston Churchill, who said, we shape our buildings, and afterwards, our buildings shape us. So we were thinking, you could look at that in a different way and say, look, we shape our buildings, we design them, we set them out, we configure them, and afterwards, these buildings will shape Eskom's peak demand. And I think this is where the load research guys will probably start paying attention to this, because if we can start understanding how our buildings or the built environment, it may be one or more buildings, can shape the load profiles on feeders, on circuits, and eventually provinces, then I think we're getting somewhere with all this fancy stuff. We start off with a very simple energy model. It's really just zones. We're looking at zones and how they interact. So we take a large building, we break it into zones, we add the floors, the roof, and especially the fenestration, because that plays a very big part. And then we start putting in the air conditioning systems and all the odds and ends that go into the building, including a whole bunch of humans to see how comfortable they are. We use a package called Energy Plus on the top left there. That's been around for decades. It's improved. It is a massive software package. AutoCAD people donated a large sum of money, and they turned it into a multi-threaded package now running under C++, I believe, and it's sped up the simulation times. In the past, we used to run a 4-core machine for 48 hours to get a model out. Now we push the stuff up into the cloud, and we run it in the Amazon's AWS, and we can run the stuff in half an hour and get a lot of data out of it. The other package we use a lot is Radiance. So all the computer graphics, Radiance is a couple of decades old now as well, put together by the famous Greg Ward. All the computer graphics you see in movies actually came from work that the guys were doing with Radiance many decades ago. And yeah, it's absolutely amazing to see what we can do now. We're starting to borrow processes and software from the computer gaming people, because we can now do real-time modeling. So on the bottom right there, you can see one single lonely little zone with a human in it. And what we're trying to do is just understand the energy flows in and out of that little box. We got heat, conduction, convection, internal long wave, external long wave, diffuse and direct short wave radiation, which is that big fireball up in the sky. And we also look at things like air infiltration, gains from equipment, heat gains from humans. Now, you're probably sitting relaxed somewhere, probably at home. Your output at the moment is maybe 80 watts of energy, okay? Or power rather. I'm a little flustered because I'm giving this presentation, so I'm pumping out about 120 watts. And we have to take all of that into account when we're trying to understand the performance of buildings, especially the thermal comfort. We also model the control systems and the actual air conditioning system. So we've got boilers, we've got heat exchangers, chiller plant, fans, pumps, you name it. We put it all together in these models, these digital models, and then we run them often for hours, as I said, and we simulate the building and the performance of the building, typically over 1 year, using files, weather files, and various inputs. Fenestration is pretty important. So we go into great detail, and you can see here on the left-hand side, we got double glazing. Some of you might have seen double glazing. I think our colleague over in Canada would be very aware of the need for double glazing, triple glazing. Pretty expensive. The question is, do we need it in South Africa? Well, this is why we model, so we can find out whether the cost benefit makes sense. So here on the left-hand side, we've got double glazing, the vertical blue bars, and then we've got an aluminium frame with a thermal break in it, and we can actually model the performance of the pane and the frame itself. And you can see we also do timber windows. On the top right, we've got a Cape Victorian casement window, and we've modeled literally thousands and thousands of South African windows, window frames with all types of glass in it, reflective glass, tinted glass, low E glass, and we look at the performance, the U value, which is an indication of the insulation capability. We also, on occasion, look at how ventilation, what airflows you can get through an open window. At the bottom image there is a thermal image showing the energy leaking out of windows, through windows, probably taken somewhere in Germany, I think. You can see that lorry is bright white, showing that it's giving off a huge amount of energy. Now, one of my weird hobbies is to travel around Sandton just before dawn in wintertime with a thermal camera and take lots of pictures of buildings, especially all these green buildings, to see how they're leaking energy. And here's another little system we use, also based on Energy Plus, this massive Energy Plus engine running in the background. But rather than model an entire building, we model a simple box. So the 5 sides of this box are adiabatic surfaces, no energy flows in and out. And the main surface is clearly the wall with a window embedded in it. And in this case, we're comparing 4 different sets of shading to see how the shading performs. We can select the shading for a given type of window, a given type of glass and window frame. And you can see the simulation 245 on the left-hand side there. that has hardly any shading. If you look at the blue bar, that represents the cooling energy needed, and then the green bar and the yellow bar, right? So the yellow bar is the amount of energy needed for lighting. So you can see that's probably not the most efficient. Then if we move to the little box, the next box up, 374, you can see it's got some shading, and it's reduced the amount of energy needed to keep that building cool, and to a degree the amount of lighting energy. I'm not quite sure why that is, but clearly the more shading you put on a building, the less energy you need for cooling that space, but you're probably going to start needing more and more energy for the lighting. So these are the trade-offs that we can model. We use this sort of thing to educate the architects as well, so they can understand the impact of different energy conservation measures. Right, next one up is something called a psychometric chart. We're very interested in the thermal performance of spaces. Okay, the productivity of humans, of the occupants of a building, is directly dependent on the thermal comfort they experience while they're in the space. So what we've got here is a psychometric chart. On the bottom, you might not read it clearly, but we've got dry bulb temperature. On the vertical, running at a diagonal, we've got humidity ratios. And these dictate, to a degree, the thermal environment for people outside. We're assuming that we're bringing this air inside. Okay, that big red dotted line is really an indicator of comfort. Anything to the right is starting to get uncomfortable. Anything to the left, to a degree, is going to be comfortable. The blue box is the ideal conditions. So this is Johannesburg weather. This is Johannesburg weather file taken an average between 1990 and 2000. And we can see where we sit. Each of those green dots represent the data from one of the points from all 8,700 or so hours in the year. Okay, and we're pretty curious to find out how things are going to be in the future. So the great thing about energy modeling is that we can now get hold of a weather file that's been adjusted to represent the typical warmer weather that we could experience in 2040, for example, and it allows us to start designing buildings for the future. There's no use in designing buildings for the past because, well, the past is over, isn't it? The world is changing. So on the bottom right-hand side, you've probably seen these little images floating all over at the moment, just showing how the world is heating up, most of it in the Northern Hemisphere. But you'll probably be aware that Australia's had heat waves. I think South Africa is pretty lucky. We haven't had any heat waves, but we do need to start designing our buildings for the future and not for the past, and we can do that using energy models. This particular model is based on the Hadley CM3 from the year 2007. If we use the current climate models to predict the future weather, I think you'd get quite a surprise. And someday we'll bring in one of the experts overseas and he'll explain the ramifications of this. Look, you might not believe in the reasons why there's climate change, but I can assure you the world is getting warmer. We're seeing it in the actual recorded data. Okay, so let's just talk a little bit about these climate files. They play a very big part when you are modeling the performance of buildings. There's no doubt that 10 years ago, we got away with using outside air temperatures. We had the minimum, maximum, average, gave us 36 data points. But as you know, everybody's living in the world of big data. So we went from 36 data points, which describe Johannesburg climate, and in no time we jumped up to 8,760 data points. That's a data point for every hour. And you can see we got various ways of communicating the weather and the climate. Visualization is very important to us because we deal on a daily basis with clients, and especially with our good friends, the architects. And they like to see things, they like to see pictures, colorful pictures. So we do oblige as engineers, okay? And in no time, we've now jumped over to minute intervals. We're now modeling sub minute to, I won't say to the nearest second, we don't often do that, but certainly to sub-minute every 15 seconds maybe. So we've gone from 36 data points 10 years ago, and we're up to 500,000 data points at the moment. And that's the sort of data and the volume of data that we're handling when we do our modeling these days. Right, so now what does it really mean? 500,000 data points versus 8,760 hourly points. Well, yeah, we got the energy usage. This is a residential building for December and January 2018. On the left-hand side, you can see the 1 minute data. And had we worked with 60-minute data, you can see the image on the right. You can't quite see the scale a bit, but the yellow area is about 600 watts, and the dark black area is about 6.3 kilowatts. So you can see the different information you get when you start modeling and thinking of the world using 1 minute data versus 60-minute data. Very clearly a big difference, and this now starts to give you some idea of what your feeders are doing if you had to attach these buildings onto circuits, onto substations. We are interested in the energy side, so let's start moving towards that. We've explained to you, you can model just about anything from airborne diseases, transfer of airborne diseases, through to the finer details of fire, and a lot of that detail. Something our guys are looking at, and by that I mean the ASHRAE, the IBPSA people, the IEEE people, they're all looking at a new animal called the grid interactive building. And there's a strong interest in how these buildings are going to coexist with the grid. Okay, we want our buildings to be good grid citizens. They should seek beneficial coexistence with the grid and work with the grid. Often it's the only grid we got. So how do we go about understanding these issues? There's a hell of a lot of research money pouring into this over the last 5 years, and we're going to see a lot more of it. So let's look at two different buildings. The building on the left is what I'd call a selfish building, and the one on the right is a grid interactive efficient building. So the selfish building uses quite a bit of energy. You can see that. The solar PV down the bottom there. Under the yellow is the actual load profile of the building. Under the green is the solar PV profile output. So they took this inefficient building, slapped a massive PV system on the roof, probably at a fairly high cost for inverters, everything. And you can see the impact, okay, on the load. The building on the right, the guy said, no, we're going to box clever. We're going to think in terms of smart buildings approach. We want to be a good grid citizen. So first of all, they started looking at energy efficiency to drop the load. And then they started looking at load shifting, moving the blue to the middle of the day when the sun shines. Okay. And we end up with this sort of load. So this is the load that the grid sees. The selfish building chews up a lot of power, and when the sun shines, it wants to inject a massive amount of power back into the grid. They call these buildings net zero buildings. And yes, sure, this can be done, but think about it. If you had 500 buildings on feeder in the middle of an urban district, and they were all trying to push massive amounts of power back onto the grid when the sun shines, that's not going in the right direction. And of course, when the sun doesn't shine, these buildings are going to be gobbling up lots of energy. And then if you look at the right-hand side there, the grid interactive efficient building, you can see it presents a much flatter profile to the grid. And that's where we want to be. Our buildings must coexist with the grid for sure. So the game we play is, we look at the building load, the building profile, and we shift, we shed, we shape, and we try our very best to provide a acceptable load profile to the grid. And that's the bottom right there. You can see that blue line That would be in many ways the ideal shape. We don't want to really force energy onto the grid unless the grid needs it. And we got to start thinking that way. This whole idea that if you put PV on the roof, you have a given right to inject as much energy back into the grid and be paid handsomely for that. That's not the way the world works. And this is one of the bigger issues the Munichs and Eskom are facing at the moment. So at the moment, and in the past, IBPSA and all my colleagues have been modeling individual buildings. We're now looking to model every building in a neighborhood, because every building in the neighborhood has got various capabilities, capacities to self-generate, and increasingly so to store energy. Furthermore, a lot of these buildings are the home to electric vehicles, and every time an electric vehicle drives into a parking lot, it brings with it a very, very large battery, and that battery can either consume energy or it can provide energy. And these are the issues that we need to start modeling. We now have to start thinking of not individual buildings, but groups of buildings, neighborhoods of buildings. So I want to show you a few things that are happening around the world. A project over in the US, they took a small city which happened to have a smart grid, lots of smart meters, a lot of data, okay? And they started breaking it up into circuits and zones, and they started modeling the individual buildings, as you can see on the right-hand side, sitting on the feeder. Some of them residential, some of them commercial, industrial, public buildings, all these various loads, to understand how these loads, with their own storage, with their own generation capability, how all of this can coexist, and of course how to get the whole business to sing together. So this particular project had around about 180,000 buildings, okay, based on real data, because remember they had smart meters on almost all these buildings. And the modeling they did, they had 3,000 independent inputs per building. And those independent inputs are typically things like occupancy, data on the building envelope, the performance of the glass, the U value, the R values, the insulation, everything including data on the HVAC system, the chiller plant, the lighting, the heat pumps, the gas. In many cases over in the States, they have gas. So they modeled all of this, 3,000 inputs per building. And then they said they didn't quite get to 1 minute data, but they said we're going to use 15-minute data, which gives you 35,000 data points per input, right? They then, well, they didn't run this on your little 4-core PC. They ran it on one of the largest computers they could get their hands on at the time. This was a couple of years ago. The Titan supercomputer sitting at PNNL over in the States took 6.5 hours to run it. And what they discovered, they can get 500 million, I converted it to South African rands, annual savings, purely by shaping, shifting, and shedding load to reduce the peak demand of the entire city, okay? And with very little inconvenience to the occupants. Because if you do your shaping, shedding, shifting, if you do that properly, you're not going to upset Mrs. Jones by not allowing her to use a hairdryer early in the morning. Okay, something that Eskom could maybe learn from all of this. So there's a very strong and growing interest in the capabilities of being able to model entire neighborhoods, entire cities even, and understanding how the energy and the power as two separate issues can be optimized to reduce the costs. Okay, now I want to introduce you to the IEEE. They've got a couple of test feeders. This is probably of more interest to our load research colleagues. If you look at the way feeders and substations are designed, there's I guess a lot of ways that it can be done to help designers the IEEE have identified a number of LV test feeders. The one we're looking at here is the European one. China are bringing some online. ASHRAE have got a couple, and Marcus will tell you that we've been talking to ASHRAE about their test feeders. And what's become apparent is that you can do a lot of good work if you had load shapes with 1 minute time resolution. So you can better understand how these circuits, how the substations are going to perform under different loads. And then you can start playing games such as what would happen if you forced every building in a neighborhood to have, I don't know, a couple of kilowatts of energy storage. What happens if you forced every building in the neighborhood to have 50% of the PV panels facing north and the other 50% facing northwest to catch late afternoon energy needed for cooling in the late afternoon? So you can play many games when you can simulate these sort of things using energy models. Okay. I was also very interested. Now, I'm new to the load research guys here in South Africa, but Bartman and Steyn had a set of slides up, I think over at the AMEU conference last year in the Cape. And they put this one up, and you can see they got integration with a question mark, and they show modeling and they show simulations, all, I guess, feeding into the load analysis and forecasting. Now, excuse me, from my side, I can certainly vouch for the value of the modeling and the simulation. So I'm going to suggest that maybe the Institute of Electrical Engineers and our colleagues around the country can put together our own low voltage test feeder. Can we identify a typical South African feeder somewhere that is well instrumented with smart meters, for example? And if we could do that and get the data, 1 minute, 5 minute, 10-minute data, we could then take all the loads on that feeder and start replacing them with energy models of the particular buildings, whether they're residential or whether they are various commercial buildings. We've got models that can model that. In fact, what we do is we borrow a whole lot of Energy Plus models from the States. We convert them to the Southern Hemisphere because clearly the sun is on the different side when you're in the Southern Hemisphere. And then we add Joburg, Cape Town, Durban weather files, and we can start simulating the performance of these office buildings. We can also start doing predictions. What would happen if you increased the insulation in the roof? And therefore, the residential people didn't have to go and buy these little 2 kilowatt electric heaters from Macro by the millions. Okay. What happens if we put a smaller geyser in, a bigger geyser, which has thermal mass and thermal storage? What happens if we did this? What happens if we did that? And all of this can be then tested, and we can see the effect on the feeder, not the effect on the individual home. By and large, we understand a lot of that, but we can see the effect on the feeder. Right, so my last few slides are really around a couple of observations. It seems to me that there's too few of us in South Africa to each go our own way. When I last did this presentation last year, we battled a little bit with the bandwidth and all of that, but the message seemed to get through, and I got quite a bit of feedback from people around the country, people working on MSCs, and all of them saying, well, you know what, it probably would make sense to have one standard, one benchmark feeder that we could all work on. Okay, and then we can all test this. Doing a peer review would be a lot easier. We can share our research, and I think we can make a lot of progress. The second point observation is we must use what others are doing around the world. I mean, these guys, we're never going to run stuff on a supercomputer, but the guys overseas are doing that on, I won't say a daily basis, but there's a lot of research that we can learn from. I haven't discussed machine learning and a lot of the technologies that our colleagues overseas are deploying and jumping into. I don't have the time, but my last plea to you is we got to move fast, guys. The country is in a crisis. We really do have to move a lot faster. And of course, you know, we are competing against other countries around the world. I do a fair amount of work out in Africa. I go to Nairobi and elsewhere, the Commonwealth countries, English-speaking countries. These guys are sharp. These guys are moving fast. Kenya's nearly carbon neutral on their grid. Amazing stuff. And here we are lagging behind. We really have to move fast. So with that, I'll leave you with this, and I'll hand over back to Marcus and Wendy. Thank you so much to the Load Research chapter for giving me a chance to come and twist your ears with a whole lot of stuff that might be very new to you. Thank you.
Oh, thanks, Mike. Very interesting presentation that you have shared with us, and I see there is also a number of questions that came from the audience. I don't want to be selfish and ask my own questions, but I will anyway. So the first one from my side that I just wanted to check is the accessibility of the software packages that you have shared there. Are these, how does one access these?
All right, Mondi, yeah, thanks. First of all, Energy Plus and Radiance are free. Absolutely free. You can go and download it tonight. It's not a massive program, although there's a lot of code. The manuals themselves are probably about 1,000 pages. That'll take more time to download. And when we last checked, there's over 8,000 academic papers written on Energy Plus and how to use it and how to do all of these things, right? So it's a massive simulation engine. The front end, the software you use to set it up and configure it and import the geometry from AutoCAD and all of that, there are one or two free packages, but normally you would go and buy Design Builder or a couple of these packages. But there's no reason at all to spend money on this. Likewise with Radiance. Radiance is incredibly powerful. It's free, a number of versions. So dig in, help yourself.
Yeah. Oh, nice. Then I will go to the first question. So I took questions as they were appearing on the chat box, and I think the first one was from Duncan. So the question was, how does the price of electricity relate to growth or decline of load? So I don't know, Mike, is it something that you'd like to take? Because don't remember seeing something related to that, but maybe you can comment.
Yeah, so I mean, there's a lot of speculation about it. I've got my own very particular opinions, and perhaps I've got a strong bias towards the grid integrated building, whereby I believe buildings in the future will generate a lot of their own power. We see it all over the world simply because the cost of moving green electrons from the middle of the Karoo to the user in Cape Town is going to be increasing. But yeah, there's a lot of questions around that. I'd rather throw that one back at you, Mondi.
Yeah. Okay. So thanks for that. I don't know whether it is safe for me to comment on that, but basically, I think Duncan also made a comment later on that this has to do with the government policy as well, because I think currently nationally we are trying to move towards feed-in tariffs, and to define those to say if you feed in during certain times, then you can bank your energy, but obviously there are ratios involved. I think I have an understanding that certain municipalities have managed to implement that, but I just don't know how successful that has been. But yeah, maybe it's just not a very safe area to start commenting on. But definitely, Duncan, your comment that came later, talking about policy, that's where it starts. We need to have clear policy that when you consume, this is what you will be consuming, and when you feed back, this is what you will be feeding back, so that you don't have to oversize your PV or whatever DR that you have on your side. You don't have to oversize it, hoping that you will make money out of that. You just need to adequately size it. And also the next one. The next comment was from Marcus.
Sorry, Mondi, can I just jump in there? Look, what we are seeing is a lot of these neighborhood energy models are being used to test policy. So here in South Africa, I think one of the NRS, I think it is 25% of your, I don't know if it's your peak load, I can't remember the details, but your self-generation should not exceed 25% of your maximum demand, maybe. So some numbers like that, okay? If you want to test policy, certainly this is the way to do it, because first of all, we can actually change the performance of each of the loads on the feeder. You know, whether it's a small office, as I'm showing you, a large hotel, whatever, we can adjust these buildings and see what effect the policy would have. So that's widely undertaken over in the States and Europe, and I understand China and India as well. Policy is often fine-tuned using these detailed energy models for different areas, because your policy for Durban might not suit the policy for Cape Town.
Okay, thanks, Mike. Now, another very interesting question here from Marcus. It's asking, you know, if you can perhaps comment on the fact that the energy managers or, you know, energy auditors can actually use the same tool, the same method to do an energy audit for a building, for an institution, to show related savings.
Yes, okay. So as you know, we're paying carbon, or we're starting to pay carbon tax. So what we often see is the use of these energy models on individual buildings to understand the effect of ECMs, or energy conservation measures, whether you put more insulation in, whether you put a chilled water storage tank or ice storage. And you can test out a lot of this beforehand to see the savings you'll get, not only in terms of energy and money, but also in terms of the carbon. And once you've done that, you can figure out whether you're going to get the tax break. You can also go out to the green banks. A lot of green money floating around looking for a good home. And if you can demonstrate you're going to be saving CO2, you'll find a lot of people wanting to lend you money at a good rate. Does that answer the question?
I think so. I mean, obviously, this is now mainly concerned about the customer. What does the customer has to save, and how do you demonstrate that the customer can actually make saying, how do you do that audit? And I think that is what you have answered. So we don't have to only concern ourselves, and so basically this doesn't only look at the grid side, but it also looks at the demand side as well. So just the next one, as we go through them, I see there are quite a few questions here. The next one is, has there been any error or accuracy evaluation that you have done here? So the question is, how typically how close is electrical load from the simulation against the measured load? So basically just looking at what you get from the simulation against what is measured. Is there any assessments on that to say this is the level of error that that you can expect when you do modeling based on this? That's a question from Marcus.
Yeah, exactly. So that's certainly something that 10, 20 years ago, the guys put a lot of effort into it, calibrating. They often built 5 or 6 over in the States and Europe as well. Germany, they built 5 or 6 identical buildings in a row on a plot of land. They had people live in these buildings, and then they used the energy models to compare how the people living in the buildings were performing compared to the modeling data. And they can model as accurately as you need. It's hard to believe that, but if you put the time and the effort into it, you can definitely get a model as accurately as needed. The biggest problems we have is in the assumptions we make, and I'll give you just one example. So with some buildings in Nairobi, we made assumptions that there was a certain level of insulation in the roof. And we were horrified when the ceiling temperatures were a lot higher when we commissioned the building. And we discovered instead of, we wanted 200 millimeters of rock wool, of think pink in the roof. And because that's unheard of in Kenya and in South Africa, the guys put 50 millimeters of think pink or rock wool. So clearly, you know, if they don't build the building the way we understand it to be, then there are going to be inaccuracies. The other issues are these pesky humans that live in the building. We make assumptions. For example, we assume all government workers get to work at 8 o'clock on a Monday morning, bank workers, wherever. In reality, they dribble in up until 10 o'clock. So clearly the models will never predict that. However, a lot of interesting research taking place using machine learning where we don't deliberately go out to build transparent models. We start putting together black box models. We don't really know what's going on inside the black box, but we take the data from, say, 2,000 buildings, 1 minute data, 5 minute data. We put it all together with some very basic inputs, such as the climate, the weather, and we let the machine learning part of it work the model out. And the accuracy can be pretty good. I've got a couple of slides. The slides that we'll distribute will include some extra slides showing the accuracy of these systems.
Okay. Thanks, Mike. So,
Mandy?
okay.
Mandy?
Yeah, go for it.
If I can just ask, I was trying to get a feeling from Mike for planning purposes of how he would describe the accuracy of his load simulation. Is it kind of within 5% of the load 95% of the time, or what typical numbers do you see with your load simulations when you describe the difference from reality that you experience?
Yeah, Marcus, I'm trying to see if I can find one of the files, but certainly, you know, these days, if we out by 5% either way, then we'd be a little disappointed on individual buildings.
Thank you. That's the kind of answer I'm looking for, because from a planning point of view, Monty, you can agree, add your view, but I would think 5% is probably good enough for planning purposes.
Yeah, I mean, even on the HBE itself that was developed to do modeling in South Africa, I think the 10% error was something that was declared to be safe enough. So I would say, I mean, at the planning stage, depending on what that 5% means and what is at stake, then it's a call that you would need to make. So I just want to go swiftly to the next question. I think it's a comment from Duncan, just again mentioning the fact that there is a need for policy. And Mike, you also mentioned that you can use this environment here to test your policy. And from the load research side, I think that is one of the tasks that I would like us to adopt and you know, see to what extent can we use this to test the policy, our policies that we have, both government, the municipality, and ESCOM, because we also do have our own. ESCOM does have their own standards and guidelines as well. So then it's just a comment. Then the next one is, if you take a standard building model for, say, it's basically situated here in Gauteng and you move it to Durban, how do you tweak that building so that it reflects the behavior in Durban? I think taking, you know, something in Europe which is above the equator, and we take it to below the equator, there is some tweaking that's required there.
All right. So look, we just make assumptions that most buildings are the same. The building style in South Africa is probably much the same wherever you go. You often get a double brick wall with a cavity wall in the Cape, but you can assume that most South African buildings are much the same. The building materials are common throughout the country. So therefore, it really comes down to, and we have the time zone. We don't have different time zones. So it comes down to the climate. And we've got some pretty good weather files, some climate files for probably 30, 40 sites around the country. Some of them are, and we use that data and feed that in. Is that what you're trying to get to?
Yeah, Marcus?
Yes, thanks, Mike. Yeah, I was trying to get a feeling for what is involved when you create an evaluation for a building which is not necessarily for that place. So my example was, say, Gauteng to Durban. What steps would be involved to get the simulation working again to within that 5% of demand or of energy? Can you just qualitatively go through the steps that you would use to move that building from the inland to the coast? Mike,
are you there?
Sorry, guys, my mic is on now. The building envelope is going to stay much the same. So the climate file actually takes care of a lot of that. There's hardly any difference in the envelope and the building structure. It's the climate file that changes everything from the altitude, the height of the building above sea level, through to the solar gain that you experience according to Joburg versus Durban. Wind, rain, all of that is factored into the count. So it's the climate file. We assume that the occupancies are exactly the same usually.
Yeah. Okay. So because of time, I would like us to just quickly move to the next one, which was from Lloyd. How can you replicate the reduction in megawatts? So basically, more interested on when you model the building, you model all the energy flows. How can we show that we will have so much reduction in terms of megawatt? And I think one of the slides here showed that when you show the bad building and the good building.
Yeah, so I mean, there's two different angles to this. Do you want to use your annual energy consumption, total annual energy consumption, kilowatt hours per annum, or you can often work that out to kilowatt.
Sorry, Mike. So this is basically to say the peak, which is the problem, and basically which leads to the actual load shedding. So the peak, the power. How do you demonstrate that reduction in the maximum demand per building?
All right.
Two curves there, yeah.
The first thing you do is you push the price of maximum demand up high so that people actually bother about it and take note of it. At the moment, our tariffs are, I guess, more focused on energy than they are on the very critical maximum demand. And once you start punishing people for ignoring maximum demand, then you will find they start doing things like like synchronizing their chiller plants, so only one chiller plant runs at a time. They'll start looking at load shifting, using ice storage and things like that to move out of the peaks. If your time of use is a lot higher, it makes it worthwhile to look at thermal energy storage. Batteries storing electrons to do the work of low-grade heat just is not viable. But thermal storage, chilled water, ice, can play a big part in moving the peaks. Does that answer that?
Yeah. In any case, I would like us to close it here. To the attendees in South Africa and out of the country. Thank you so much. Thanks for your time. Till we meet again.